kinds of systems, or AX equals B tilde. But if this has a component in the null space where you do not have a solution, that part will not go to 0.
Will you say that again? The last part?
Yeah,
Okay.
the last part is,
All right. So if your initial error has any component in the range of A, then continue multiplying by n inverse n, that's going to drive that part to 0. But the portion of your initial error that's in the null space of A, you're not going to, that part will not go to 0. And it's because of the answer to part A of this problem that you can see why.
thank you.
Okay. Now, because what will happen is, if you happen to use your iterative method on this singular system where B already is in the range of A, your iteration will converge. But when that doesn't happen, and you see this difference between iterates not going to 0, you have to see, well, what is it converging to? What is happening to that difference between iterates? In fact, it might not be a bad idea in MATLAB or Octave to go ahead and try the example from part C and actually try the iteration out on the original system. You'll see it won't converge, but you'll observe some interesting behavior. And that could give you insight onto, yeah, because you can try looking at this theoretically, or you can try looking at it in code. And it might actually be easier from experimentation to see what is the actual behavior when you try this in a singular system. Oh God. I am in so much trouble time-wise. Oh, and Dr. Perry wants to talk to me after class, so that's going to be fun. Okay. I have to keep going. So, well, we'll see how this goes. I might be able to make up for it next week, but okay. So the final assignments, I have this programming project that's already posted. But on Monday, I will post an alternative homework form that is more theoretical problems about eigenvalues. So you can do either assignment. Depends on how you feel about coding. Okay. Now, we will get into, finally, numerical algorithm. If I have time today, I'll look at 8 There's also 8.3. So I'm kind of going to go back and forth between two chapters. I'll spend most of my time in chapter 7 on general eigenvalue problems, but chapter 8 is about the symmetric eigenvalue problem, the topic of assignment 4, where a lot of simplifications happen. Okay. So the idea is so assume that we have a general square matrix A that has these eigenvalues, where I'm ordering the eigenvalues by absolute value. These could be complex. So lambda 1 is the largest. And we assume that there's a unique largest eigenvalue. So I have greater than or equal to everywhere else, but it's strictly greater than here. That's going to be important. I'm going to apply the power method to matrix A. So what I do, so I choose some vector x naught. Actually, to be consistent with the notes, I'll call it q naught. At least I won't use any little a's here. And I'm going to make q naught be a unit vector in a two-norm sense. And then alright, so then I keep iterating. I multiply my vector qk by a, and I'll call the result zk. And then I get my next vector, qk plus 1. I just normalize that vector. So all I'm doing is multiplying by a, normalizing, multiplying by a, normalizing. I just keep doing that. And that is the whole method, the entire power method, until my q's that I'm generating converge, if they converge. That's it. That's the whole power method. This is actually the algorithm that is used by Google on a matrix representing the entire web that you...
PageRank?
Yes, it's a PageRank algorithm that each entry of a matrix represents a probability of going from page I to page J in just one click. So if you take powers of that matrix, that's the probability of going from page I to page J in whatever number of clicks. Most of the entries are 0 because you can't go just anywhere from anywhere. And what's of greatest interest is the eigenvector corresponding to the largest eigenvalue of that matrix, which gives probabilities of ending up on any page. And that is used to rank search results. So what is this method actually doing? It seems strange that just multiplying by a continually is actually going to accomplish anything, but often it does. So we'll take a look at that. Okay. Now, to simplify the analysis, I'm going to assume, whoops. Okay, so I'm going to assume A is diagonalizable, so it has n linearly independent eigenvectors. Okay. And what that lets me do is I can express my initial vector q naught as a linear combination of these eigenvectors. So now I can look at qk. So that is some constant, which I'll call beta k, a to the k q naught. Now the beta k is just some scaling factor for normalizing, so it's not really important to this analysis, but I need to put it there anyway. So if I keep in mind that these x's are eigenvectors, then what I get is a sum of ci lambda I to the kth power xi. But now what I'll do is I'm going to multiply and divide by lambda 1 to the k. So I have lambda 1 over itself raised to the k power. Now the one that's in the denominator I'm going to leave there, and the one that's in the numerator I'll pull out. So I have beta k, lambda 1 to the k, and then I have this sum of ci lambda I over lambda 1 all to the k power. Okay. But now what I'll do is I'll break up this sum. So the first term, this exponentiation will become 1. So I'll have c1 x1 plus a sum from 2 to n, lambda I over lambda 1 to k xi. Alright, so this is what's happening as I keep multiplying by A and normalizing. Now, if we focus on just this sum here, keep in mind that lambda 1 is the largest eigenvalue of the bunch. What's going to happen to this as k goes to infinity?
Smaller and, well, okay, larger.
Most of this is going to 0, but what's left? Not everything goes to 0. Well, what exactly is going to 0? Yeah, the whole summation is going to 0.
Yeah.
But that doesn't depend on k at all.
Oh.
Yeah, so that part is going to stick around. So, so this converges because to a vector that is parallel to x1. So this is what the power method, because all components of all other direction of all other eigenvectors are going to go away. So the conclusion is the power method is useful for finding the largest eigenvalue and eigenvector. Now, really what it does is it finds the eigenvector, but once you have the eigenvector, you can just do a simple computation to get the eigenvalue. All right. So this is a good start, that we have at least a method for extracting an eigenvalue and eigenvector. And then what you could do is perform deflation, like I illustrated on Monday, to get that eigenvalue out of the picture, and then we could work on a slightly smaller matrix to find the largest eigenvalue of that, and so on. So I have a couple files on the site, power method .m, and then findigs.m. This is a crude approach for finding all the eigenvalues. Power method will implement what I just showed you and find an eigenvalue. Findigs shows how, at least for certain matrices, you can use deflation in conjunction with power method to find all of them. It's not really an effective method, but at least builds on whatever ideas I've already shown you. And then I'll get through the rest of today and next week, we get into more sophisticated methods. Okay. Now, let's see how awful I'm doing on time. Okay. Now, first I need to point out some one big drawback of the power method. Actually, a couple big drawbacks. Okay. First is, what if A does not have a unique largest eigenvalue? So suppose you have a case where you have two eigenvalues that are the largest. They have the same absolute value, but they themselves are not equal. For instance, maybe they have opposite sign, or maybe they're complex conjugates of one another. In that case, the power method fails. What you get is, you keep getting a different vector that's in the invariant subspace corresponding to eigenvectors for both lambda 1 and lambda 2. The trouble is, it doesn't converge to any particular vector. So you move into some invariant subspace, but that's all you got. So there's really nothing else the power method can give you. Now, even if you don't have this problem, another problem you do have is